Okay, thank you, Peter. So everybody, nice welcome to my presentation. Can give you some background information. I wanted to join the conference like 3 weeks ago, but then the application deadline was already expired. So I wrote to Peter if I could join the conference. He said yes, and at the same time he also asked if I want to do a presentation. And after some thinking and some time, I said yes. And so I did a presentation now on the CFD process at MBDA and the possibility for higher order methods. Yeah, my presentation is structured in 3 parts. I first tell something about MBDA and what we are doing, and then I present our CFD process and then some applications of CFD for our products. And I hope I can sometimes bring the focus on possibilities for high order methods too. So let's start with MBDA. Who are we? We are the European System House for Guided Missiles. And we have a strong presence in Europe, especially in the countries of our 3 shareholders, which are Airbus, BAE Systems, and Leonardo. So you can find us in France, in the UK, in Italy, and in Spain, and also in Germany, where the main site is in Schrobenhausen, which is close to Munich. And here you see an aerial picture of our site here in Schrobenhausen. And usually my office is in this, this building, but today, of course, I'm in home office. Then how we are structured as MBDA in the development department, I would say that we have in all countries, especially in France, in the UK, and in Germany, missile development departments. That is because that we are a defense company, and sometimes we have projects which are nationalized only. And I myself, I'm in the missile design or missile pre-design department, where we do the pre-design of missiles and also aerodynamics and CFD. And from 20 people who are working there, I would say 3 people are doing CFD or aerodynamics permanently. But I would say 6 more people have a strong background on CFD and aerodynamics. And yeah, I'm one of these 6 guys, I would say. I myself studied mechanical engineering in Munich, and then I did my PhD thesis in Stuttgart on discontinuous Galerkin in 2016. Afterwards, I worked for another defense company called Rheinmetall in Germany, and there I did CFD for tank and artillery ammunition. And since 1.5 years, I work at MBDA. Now to some products and the markets we are in. First product or market is the ground-based air defense. There we have in Germany the TLVS system. It's an air defense system which is developed together with Lockheed, and it should be the successor of the Patriot, the well-known Patriot system in Germany in the future. Then we build missiles for fighter aircrafts, I would say. Here we have a cruise missile, the Taurus, which is in service in the German Air Force and other air forces in the world also. And then there's the Meteor missile, which is an air-to-air missile, which is developed in Europe jointly, I would say, and is in service in many countries in Europe. The specialty of this Meteor missile that it is propelled by a ramjet propulsion. Here you can see the inlet of the ramjet, and that enables the missile to travel up to 200 kilometers with a speed of up to Mach equals Mach 4. And so this is not a missile for dogfight a la Top Gun. It's a missile where you can engage an enemy fighter beyond visual ranges, I would say. Then we are also in the market on missiles which can be used on the ground. For example, there's this enforcer missile, which is used by soldiers, and we have missiles which are more like rocket artillery, I would say. And then we have also missiles which are used on ships. For example, here this ram missile, which can defend the ship from incoming missiles. And I want to come later to all of these products again, where I will show some application of CFD in one of these areas. I will do it for the ground-based air defense, for the fighter aircrafts and these battlefield missiles, but not for the ship missiles. But before that, I will show you something about our CFD process. In the first step here, I will present some characteristic features of the flow we are dealing with and the requirements for CFD solvers which we have. First of all, we have a high velocity range. It basically starts at 0 velocity if you think of ground launch of missiles, and then it goes to subsonic and transonic range. It's especially for turbojet propelled cruise missiles, and we have supersonic and hypersonic missiles. And that requires for our CFD solver that we are robust in all velocity regimes, that we have an efficient shock capturing. We need turbulence modeling and sometimes transition modeling also. Then we have, the missiles fly on different flight altitudes. It starts at sea level and can range up to the higher atmospheric levels, up to 80 or 100 kilometers, where we sometimes have to think about a rare feed gas dynamics approach also. Then we have different flight conditions, different angle of attacks, different roll angles, radar deflections. So for a missile, we have to simulate quite a lot of data points. And so we need a high grade of automatization here and also a high prediction quality. For example, for a high angle of attack, which can be in the range 20 to 40 degrees for a missile. Then we sometimes deal with chemical reacting flow and multiphase flow. This can happen in engine or in attitude control systems. Especially to these attitude control systems, I will show some application later. And this needs or requires the solver to be able to handle real gas modeling or non-equilibrium flows with chemical reactions. And then we have also steady and unsteady flow. That means that we need in these conditions fast convergence. And in unsteady flow conditions, we also handle sometimes rigid body movement or deformation. Rigid body movement, if you think about separation of missiles from fighter aircraft, for example, or deformation of wings, for example. The next slide is about our current CFD toolchain, which we use. If we get a CAD model, in the first step, we use a program called CutFix. We use it for cut cleaning and for the naming of different parts of the missile, which is needed for the measure and also for the later post-processing. Then we have different meshing tools. We have a license of the ANSA mesher, but we don't use it very often. Instead, we use a mesher which we bought from Airbus Defence and Space. And it is script-based and so quite flexible for us. For example, if we only want to change the rudder deflection of a missile, like here, we can do this in CutFix quite easily, and then just change the name of the input file in the meshing script and remesh our missile. As a CFD solver, we use the TAU solver from the German Aerospace Center, the DLR. I think it's widely used in the German aerospace industry, and also our colleagues at MBDA UK use it. Then we have Linux clusters with 4,000 cores. And the post-processing we do with Tecplot, Python, and MATLAB. I want to give you now some overview over the Tau solver. Regarding the discretization, it's a second-order finite volume solver. For Flux Discretization, we have a central and an upwind scheme. The upwind scheme can use the Rowe-Riemann solver or the Osem or von Leer scheme. Then we have a wide variety of turbulence modeling possibilities. And we can do unsteady simulation with dual time stepping. And we have a multi-grid acceleration. Regarding the mesh or the cells, it's an unstructured hybrid solver. We can locally adapt our mesh, for example, here in the presence of shocks. And we can also adapt the Y normal or the wall normal direction to have an optimal Y plus value. And it's parallelized via domain decomposition. And other features which are nice in the solver, that it supports the chimera method, especially for large rigid body movement and grid deformation. And we can also handle non-equilibrium gas flows with chemical reactions inside the solver. So that was about the solver. And now I want to present some different applications of our CFD process. And I want to start here with some results which we got from our Enforcer missile. What is our standard business here is that we have to do CFD calculations in order to get aerodynamic data sets of missiles. And this can be quite extreme for the final product, so that we have to simulate up to 200,000 data points for such a missiles. For example, different angle of attacks, different roll angles, or different rudder deflections. What we also do here with our CFD solver, that we analyze the loads and the bending moments, for example, here on the fins, and that can be used for further structural analysis. And what is also sometimes done here is that we analyze dynamic derivatives like pitch damping moments. This can be done if we give a sinusoidal movement to the missiles and analyze the coefficients then. This is our standard business, I would say. And another topic I have here is in the ground-based air defense area. And it's about the interceptor design of interceptor missiles. One key feature or requirement, if you want to design an interceptor missile which is able to intercept other missiles or air vehicles in general, is that we need a high maneuverability for these interceptor missiles. And this can be done either by so-called attitude control systems. These are more or less pyrotechnical devices which produce a lateral jet for controlling the missile. And for example, here for the PAC-3 missile, which is part of the TLVS system, these systems is placed here. And for the Aster missile, these systems are placed inside the wing here. Other possibilities to have high maneuverability are aerodynamic devices like vanes and fins, of course, and also thrust vector control. But here I want to concentrate now on these attitude control systems. It's almost impossible to design such systems in wind tunnel, so we need simulation here. And these simulations faces a lot of challenges. For example, one question is how to design such systems. How many jets do we need? How many or where should we place these jets, or how long should the thrust be active, and so on. That are all questions on designing such a system. Then there's always the question, what is the influence of such systems on the wings and fins? For example, in the Aster missile, one of the reasons why these systems are placed inside the wings is that the jet does not interact here with the fins. However, we need aerodynamic data sets in order to control the missile if this jet is online. And we have here a lot of modeling challenges, I would say. One challenge is, for example, or one question is where we should start with our simulation. So should we model the nozzle, or could we start with some boundary conditions here? Then what model should we use? Should we use single flow? Should we use chemical reacting flows or two-phase flows? Should we consider the altitude influence, that these systems depend on the flight altitude? And should we consider also different operating conditions, like full thrust, or only 50% thrust? I have now a simulation result which I did. It's a pre-design of such a system where I have placed 4 nozzles in the front of the missile. I simulated it within the supersonic regime at different flight altitudes with a k-omega turbulence model. And I did this with different angles of attack, of course. One result, which you could see here, is that these jets have a huge dependency on the flight altitude. If the flight altitude is increased, the influence of the jet gets a bit stronger, or has a different influence than compared on a lower flight altitude. And one result I also have here is, if you look at the lift coefficient over alpha, the angle of attack, here I have in the red line, it's that the jet is not on, that the attitude control system is not working. Then the blue line is with 50% power, and the other 2 lines are with different turbulence models at 100% power. And if you compare these jet on and jet off conditions, you sometimes see that the lift coefficient is almost the same, but sometimes there are differences. So we would need here a new aerodynamic data set to model the missile aerodynamics. Yes, and that is possible also an idea for study with high order methods, I would say here. The next thing which we do in the area of ground-based air defense is also that we look of possible threats. For example, last year we did some simulation about the Russian Kinzhal missile, which is a hypersonic missile. And before that, we also looked at hypersonic glide vehicles. They are really fast missiles or air vehicles. We simulated it up, for example, here at Mach equals 10, Mach equals 20 at different altitudes, here 30 kilometers, here 50 kilometers, and with different gas properties. Here's an ideal gas law, and here with chemical reactivity. And you see there's lots of difference in the temperature field around these air vehicles. Depending on the height, but also depending on the gas law you use here. And we also are interested in the thermal heating or the plume characteristic of such threats. For example, you see some validation calculations which a student did recently. We have here some results from cones where experiments are present. And for example, then we evaluate the heat flux in the simulations and compare it with the experiments. And here you see the influence of the turbulent intensity in the free stream on the heat flux in this transition model. Another part of work is the design of missiles for fighters. And of course, sometimes we have here different design drivers, for example, endurance, range, or speed, or stealth design, agility, flight altitude. But we have to handle all these different design drivers in our CFD simulation. For example, if we want to accurately predict an aerodynamic data set for endurance range, we need quite good values of lift and drag, I would say. What we do also here is that we study inlets, for example, here a ramjet inlet, and also engine jets. And another topic, what we do here is the release of missiles or the separation of different stages. For example, if a missile loses its booster stage, then we can do this either with a quasi-steady approach, but we are also able to do it with a full unsteady approach in tau with chimera grids. So in this topic, maybe we didn't do so much in the last years, but it's a coming topic if you think about these new fighter programs, which are now starting in Europe, for example, the FCAS fighter in Germany and France and Spain, and the Tempest fighter in the UK. So this was my presentation. I hope you saw that we use a lot of CFD for our problems, which are sometimes quite challenging. And my summary is then that CFD is essentially for missile design. It reduces dramatically our costs and development time compared to wind tunnel tests, I would say. And we are able now to handle many problems or tasks with high quality or accuracy. But nevertheless, there's still room and possibility for other methods, for example, high order methods. And I would divide the possibilities for high order methods in two categories. I have here these vortex dominated flows. For example, the interaction of wing or body vortices with the radars, especially at high angle of attack. And of course, combustion and mixing, which is important, for example, in the ramjet propulsion, or missile release, especially, for example, from helicopters or so. And the other topic which I see is physics-dominated flow. For example, these attitude control systems, which is basically a jet and crossflow. Then engine jets, which are mixing layers, I would say, and also transition prediction. And yeah, also what Peter said, that yeah, computer systems are also changing. It's especially interesting, I think, also for our companies, because we are starting to upgrade to yeah, GPU-based systems, not for CFD, but mainly for artificial intelligence or yeah, image detection and so such algorithms. So there would be some yeah, some possibilities to share these clusters and also to save costs, I would say. Yeah. So this was my presentation. If you have any questions, feel free to ask. And I want to thank Peter for giving me the possibility to talk here. And of course, if you have further questions which cannot be solved today, you could also write an email to me.